So these are the activities we did so far. We started with the fraction 1/2. That was the first fraction. And we created a second fraction, 2/4, by multiplying the numerator and denominator by 2. We got the 2/4. And then on the number line, we realized, well, 1/2 is same as 2/4. And then we said, let's do a second activity. Let's keep the fraction 1/2, and this time let's multiply the numerator and denominator by 3. And that's how you got the second fraction, 3/6. Once again, on the number line, we discovered 1/2 is exactly same as 3/6. Now you might be wondering what happens if you multiply numerator and denominator by 4 and you created a second fraction, a new fraction. What would that fraction be? 1 times 4 is 4 and 2 times 4 is 8. This is the fraction. And perhaps you're beginning to think, I bet 4/8 is exactly same as 1/2. You're correct. And if you're not sure if that is the case, then I suggest you repeat that activity again. Draw your number line, mark off 1/2 and 4/8 on it, and see, make sure they're exactly the same point. And if you begin to believe it, that's the case, perhaps you're guessing 4/8 is same as, can you guess? So let's see. To get this fraction, we multiplied numerator and denominator by 4. The next one, multiply numerator and denominator by 5. So continue on and so on. And you can keep going like that. And the second activity, another activity we did was, we said, let's not start with 1/2. Let's start with another fraction. And the fraction we considered was 2/3. And then we said, let's multiply numerator and denominator by 4. And that's how we got our 8/12. And once again on the number line, we showed that when we plotted 2/3 or 8/12, they were exactly the same point, same number. That's why we put an equality sign. And you can choose to multiply the numerator 2 by not just 4, by another number, and same thing denominator 3, not just by 4, by any other whole number. What do I mean by that? I could probably multiply 2 by 5 and then 3 by 5 and get a new fraction, and perhaps you're guessing the new fraction I get is not going to be some other new point. It's going to be exactly matching up with 2/3. That's perhaps your guesswork just based on the activities we've done so far. And if you're guessing that, you're right. If you're not sure you're ready to guess, then I suggest you pick another number, such as maybe 3 and 3, and then multiply. So 2 times 3, that would give you 6. 3 times 3 is 9. So look at 6/9, plot 6/9 and 2/3 on the number line, and see if you get the same point or not. And if you're at a point where you say, yes, I really just am beginning to get the gut feeling, put any number, same number here, and the fraction you get is going to be exactly the same point as 2/3. Then here's what we can do. Instead of putting a specific number like 5 or 6 or 7 or 8, I'm going to use a letter, N. And N. What is N? And here I'm going to say, for any whole number, N. So N is a letter I'm using to let you know you can pick any number, any whole number you like, and multiply the numerator 2 by that number and 3 by the same number. By using the same letter, I'm indicating you have to multiply the numerator and denominator by the same number. And I'm beginning to just make this wild guess that whatever N you pick, and it has to be the same whole number that you pick here for here and here, and you create your new fraction. We're beginning to be bold and say, I bet that's going to be same as 2/3. Why is that? I don't know, but I just have this gut feeling because I've done this experiment here. I checked 1/2 is 2/4. I checked 1/2 is 3/6 on the number line. I checked 2/3 is 8/12. I know I could do more checking of this kind, but I just feel this is going to work. Do you guys feel that? If you feel that, that means you're making what mathematicians call a conjecture, an intelligent guess, and a generalization just based on some simple examples. You just checked 1/2 is the same number as 2/4. 1/2 is the same number of 3/6. 2/3 is the same number as 8/12. Those we actually checked on the number line. Now you're just making a wild guess that maybe any fraction you pick, say that's your first, so let me actually write that down. Say we pick 4/5 actually as a fraction. And you're saying, I bet if I were to multiply 4 by n, which is a whole number, and 5 also by a whole number n, so for any whole number n, if I were to do that, that new fraction, I just feel it's going to be exactly same as 4/5. That could be your gut feeling. If it is, that's a conjecture, and let's state it out here on the other board. So those activities, the 3 specific examples we did, were kind of making us think that we may make a general guess, which I call a conjecture. So tell me if those specific examples support this statement I wrote here or not. Let me read the statement for you. A fraction is unchanged when we multiply its numerator and denominator by the same non-zero whole number. So what this means is, if you start out with a fraction and you create a second fraction by taking the first fraction and simply multiplying the numerator and denominator by the same whole number, which is what we did in the examples, then this conjecture is saying, well, you didn't really get a new fraction. It's still same as the old fraction. Unchanged means the first fraction and the second fraction are talking about the same number, same point on the number line. So if you were to plot the first fraction and your second fraction, they would be the same point on the number line. So that's what this means to say a fraction is unchanged, means it's the same point, same location on the number line when we multiply its numerator and denominator by the same non-zero whole number. So definitely our 3 examples make us think, yeah, I feel this is true, and this is what a conjecture is, because you're just guessing it. And when mathematicians make a conjecture, they have to prove it. It's just the examples had them guess that I bet this is going to happen, and then mathematicians go ahead and prove it. I won't show you the proof today, but this statement is true. Mathematicians have proved it. And the examples we did are not exactly a proof, because we worked with very specific numbers. And this statement is about any fraction. Doesn't matter which fraction you pick. If you were to do this activity, multiply the numerator and denominator of that fraction, it's not really a new fraction. It looks like it's new, but if you plot it on the number line, it's exactly the same point as the first fraction that you started out with. So this statement is so important, it has a name. We're going to call it the fundamental fact about equivalent fractions. The equivalent refers to the fact that the 2 fractions, the first and second, are equal, and sometimes we use the word equivalent. Equivalent means exactly same as equal. You saw when we plotted it, the first fraction and second fraction were equal. We can say the first fraction and second fraction are equivalent. Just a word that means same as equal. And let's use this FFEF, fundamental fact of equivalent fractions, to refer to this. So in the future, when I say by the fundamental fact of equivalent fractions, or apply the FFEF, what I'm saying is, hey, you have a fraction. If you don't like how it looks, go ahead and multiply its numerator and denominator by the same non-zero whole number. And don't worry about it. The new fraction you get is exactly the same as the first fraction you started out with. So recall the fundamental fact about equivalent fractions, which I stated as an English statement. Sometimes it's fun to state the same English statement using symbols in this manner. This is how sometimes mathematicians write it. So if you're up for this, 5th graders and higher, I think we're ready to introduce you to using letters. And I'll go through it and I'll explain you how mathematicians use letters, and more importantly, why we sometimes use letters. So let me read the statement for you. It's conveying the same information as the sentence that I gave you earlier. Suppose A and B are whole numbers and B is not equal to 0. For any non-zero whole number n, this equation is true. What is this equation saying? Start out with your first fraction. This is just like the activities we did, but except here we're using letters, A over B. The reason we are using letters is, I want to say it could be A could be 1, B could be 2, A could be 4, B could be 5. So by using A over B, I'm saying that's any fraction that you can think of. You can choose your own whole number value for A, choose your own whole number value for B. That's why I had to tell you earlier what my letters were. I can't just use letters without telling you what they are. So A over B is my first fraction. Now I'm telling you that's exactly same as what we discovered. What did we discover? We said you can multiply the numerator A by your favorite non-zero whole number, denominator B by your favorite, the same non-zero whole number. That's why I use the same letter n and n here. So once you pick n to be 7, then you have to use the same n here, 7 here. So this equation will always be true. A fraction A over B will always be equal to A times n over B times n, whatever n you might pick, and then whatever A, B you might pick. So when you see the same letter, if you see A here, they're denoting that same number, okay? And remember this equation, don't be too afraid of the letters, because we actually did an example where, let me match the letters with the numbers. Remember, we've showed on the number line and in the on the number line, I showed you that 2 over 3 is equal to 2 times 4 over 3 times 4. 2 times 4 is 8, 3 times 4 is 12. So I showed you on the number line 2 over 3 is exactly equal to 8 over 12. So here, this example, the same as this, A is 2, B is 3, and N is 4. So don't be afraid of letters, because letters are exactly numbers. And when you use letters, we must always say what those letters are representing.